Well, welcome to the second video where I explain the use of the Cohen-Clevenger expression for the simulation and modelling of continuous thickener design at Particles Org UK. This is the second video. It follows on from the first one. In the first video we actually looked at the Cohen-Clevenger model. In this instance the video is entirely looking at the force balance regarding settling solids and the permeability of those settling solids. So the actual simulation is at this particular URL, and it is the force balance that I'm considering, and also how we can use the predicted permeability without actually having to do any tests. This is really a book design of a process, but I do go on to compare the permeabilities from the prediction against some experimental data. So we'll see a comparison between data and prediction as the time goes on. Well, a quick reminder about what we're trying to do here. What we're trying to do is to obtain the plan area, which is this area here. So if I draw that to be something like a diameter, then it's this total area. Imagine yourself looking down onto the circular cross-section thickener. So the plan area is going to be a circular area, and that is essentially what the design is all about. That's what Cohen-Clevenger's equation is all about. And then we'll be looking at a force balance of solids that's settling in the hindered settling regime inside the device. This device is a continuous device. We're continually feeding material in. Material is overflowing, hopefully with no solids. All the solids come out the bottom section here. So it's a continuous device. But in order to design these continuous, very large devices, we do laboratory tests. So the classic lab test is a batch sedimentation test done in a measuring cylinder of something like 500 millilitres or a litre capacity. And what we're looking for is this interface. So we're watching this interface settle. And initially, with certainly incompressible materials, we get a linear rate of fall of that interface, and that velocity of the linear rate of fall is what we call the superficial velocity, which we will be calling U0. Okay, so here are the sorts of laboratory tests that we can do, simple laboratory tests that we can do, that should predict the performance of a large-scale thickener, and particularly the design area of that thickener. And this is all determined, this is all based on the fact that the settling velocity, what I called U0, is a unique function of concentration. Okay, it is not a function of the area of the vessel, it is solely a function of the concentration, a unique function of concentration. Hence we can do these tests in a laboratory batch cylinder, and the results, the settling velocities, are relevant to the much larger area industrial thickener. So again, the force balance that I'm talking about is a force balance that we'll do inside the batch cylinder, and that should actually have the same principles as the force balance inside our continuous thickener that we have just here. Well, in the previous video we arrived at this equation here for that plan area. This is the Cohen-Clevenger's equation for plan area, where U, well, it should really be U0, because that's what we're using in the future. U0C is the settling velocity as a function of concentration. You're not, C isn't multiplied by U0 there, that's just the value of U0 at different values of concentration. Why is it written like that? Because we are looking at concentrations between the feed value and the underflow value. So we're having to put lots of different concentrations into this equation and work out the plan area from those different concentrations. Apart from that, we have the feed rate, which would be meters cubed per second. This is the original concentration going into the thickener. So we're having to use this equation again and again and again, simply changing the value of C just there and U0C just there, changing those values from a value of C0, the feed concentration, to Cu. That's the Cohen-Clevenger approach. So clearly we need an equation for U as a function of C, or U0 as a function of C. And in the previous video, the old technique for solving it was given, and that is based on the Kozeny-Kármán equation, because what we have just here is permeability according to Kozeny-Kármán. Okay, Kozeny-Kármán is a well-known equation, well-known permeability expression. What are the inputs for the Kozeny-Kármán equation? Well, concentration. We could be expected to know what the concentration is, at least between the C0 and Cu, the feed concentration and the underflow concentration. So C, expecting an input of concentration, isn't too troublesome. What about SV, specific surface area per unit volume? Not too bad, because if we assume spheres, it's simply 6 over particle diameter. Okay, and I'll give it a little subscript. So that's the SOTA mean diameter, 6 over the SOTA mean diameter, so particle size. So it's reasonable to assume that we know the size of particles that we're trying to design the thickener for, or that could be estimated from taking a sample and measuring it. However, it's a 3-parameter model, and this is the parameter that causes the problem, the Kozeny constant, big capital K, which has a book value of 5. But that value is for close packed materials. It's for consolidated beds. It's the sort of thing you might have in packed columns, possibly in filter cakes, but is a very weak assumption to be 5 for loose beds, moving beds, things that are relevant to hindered settling. So previously we've looked at K being a function of concentration. We know it's a function of the types of material, so we know that K is also a function of the type of material, the shape predominantly, type of material, but we also know it's a function of concentration. So it's a weak model really, because there's too many imponderables. We don't really know enough about K. So it's now being developed. The technique that we now have at this website now avoids the Kozeny approach. Okay, well, how have we avoided the Kozeny approach? Well, the first step is to go back to the equation in its base form, the form where instead of having substituted in something for permeability, we're just leaving permeability there. We will need a permeability model, but I'll mention that in a moment. But the first thing I want to do is to explain where this equation comes from. Okay, I mean, this is in fact a force balance. So how do we arrive at this equation? What are the assumptions that this equation is relevant under? They're the important things to tackle next. Okay, so here is our force balance, and what we have just here is our settling suspension, be it in the batch cylinder or in the continuous thickener. So delta H is a small but finite height. Okay, and then here are our 3 terms. What we have here is the solid stress gradient. So that's the solid stress. It's the reaction force, essentially. So here is the solid stress gradient, that's P subscript S for solids pressure. And there is a solid stress gradient with respect to height, clearly a differential, but we're multiplying by our small but finite distance, and if we multiply by area, bearing in mind that is a stress or a pressure, that'll be newtons per metre squared, so that will be newtons, and the heights cancel out. So we've got the reaction force. This is the force underneath the solids. Okay, so the solids are clearly going to have to be sitting on each other's shoulder. There has to be that solid, for that solid stress gradient to exist. And then we have the weight term. So just here we have the weight term, which is obviously acting downwards, and the weight term is always present. Okay, what do I mean by the weight term is always present? Well, there's always a certain value of concentration, the acceleration due to gravity, the density difference, because we have a buoyancy force which we've brought into this expression here, and then again this is per the area of our layer that we're looking at, and the small but finite difference in height. Okay, that exists under all conditions, whether we have sedimentation or whether the particles have settled out. Okay, what's the relevance of that? Well, whilst the particles are settling, we want the weight force, or we expect the weight force, to be balanced by the liquid drag force that's just here. Okay, so this is basically coming from Darcy's law. Here is our drag force, where mu is the liquid viscosity, k is the permeability, that's the velocity, the settling velocity, u0 for the solids, and again we have a delta h. Clearly we can cancel a delta h out, although we no longer are in the units of newtons, and we can rearrange for u0. Okay, but before we do that, we need to take this out as well. So in other words, what we're saying is that so long as the solids are not supported by a layer of solids below, then we should be able to simply equate the solid's weight with the liquid drag, and that's relevant for the initial constant rate settling period. So in that particular period we have just two forces, the weight force, which we always have, and the drag force from the liquid, and that means that by observing the height against time plot and taking the gradient of the height against time plot, that gives us the settling velocity. We can't do that though when we get to the curved section, and certainly not when it's at the nearer the stationary section. That's when potentially these forces come into play. So initially in this constant rate period we have just weight and drag. However, in the period when it's fully settled, then we have no drag, and at that stage we do have the solid stress, because the solids will come to an end. They'll be not settling anymore, so there's no motion, there's no drag, but of course the solids are now sitting on each other's shoulder, so we have that stress gradient. So here are our three forces: always weight, but drag relevant to the initial stages, stress relevant to the later stages. It is of course the initial stages that we want the data for our process. Okay, so in the initial stages then, in our batch settling, we have our equation for settling velocity as a function of concentration, and here it is. We left permeability into the equation. Of course we do need a permeability model, and the favoured model now is the one based on Happel and Brenner rather than Kozeny. Why? Well, we only have two parameters: the concentration, which is something that we're investigating anyway in the design from C0 to C underflow, and we also need to know something about the particles, the SOTA mean diameter of the particles. There's no other empirically fitted parameter inside the equation, so the objective of moving to this approach was to get away from arguable fitted parameters inside the equation. However, it does mean that we are critically dependent on knowing the particle size. It's squared, so it's heavily dependent on the particle size. Okay, well, I've mentioned Kozeny-Kármán equation. That's how we originally started with the simulation. We now use the Happel and Brenner approach. There is another alternative, which is to follow the approach of Richardson and Zaki, who came up with this empirical equation that correlates the velocity u0 and the terminal settling velocity and 1 minus the solid's concentration to the power n. Well, what does that mean? Remember, we're talking here about u0 being a unique function of concentration for a given material. I slipped in that for a given material because in this equation that for a given material comes into ut. We might be able to use Stokes's equation, which relates the particle diameter to the terminal settling velocity just there, and of course the density of the material, the viscosity of the liquid. So that's what I mean for a given material under given conditions of concentration. And here is the height of the interface that is again illustrated in this plot over here. Here's the height of the interface, and we can see this is for 3 different concentrations. So this is the highest concentration because it is the slowest one. This is the lowest concentration because it's giving us the highest settling velocity. So we could just use this equation inside the Coe and Clevenger equation. It gives us u0 directly. No need to go via permeability. But yet again, we're stuck by an empirical parameter. Arguably, this could be terminal settling velocity, so we could calculate that from Stokes, but we have no prior knowledge about what the value of n is. Book value 4.65. It does vary from 4.65 down to 2.2 in the book, but I have never seen n less than 5. And in fact, n normally varies practically up to all sorts of values. It can even go up to something approaching 100. So again, we have a technique which, if it worked, it would be a simple technique, but unfortunately we're stuck with, again, without any experimental data, not knowing the value of n to use in the model. There's an empirical fitted value again, which we don't really know much about. Well, okay, just how good is Happel and Brenner then at predicting permeability, and what sort of behaviour should we expect from a permeability model in hindered settling, where the bed isn't closely packed, it isn't consolidated, it's a loose bed with gaps between the particles. Okay, well, here is some data. We've got actually 4 bits of data. There's 2 more on the next slide. Apologies that you won't be able to read it, but what we have up here is particle size. So it's in fact the SOTA mean, what I'll call the SOTA mean diameter, plotted against concentration. So we've got concentration this way. And this is for a material called Ballatini, which are glass beads. And you can see on the right hand side an image under a microscope of the glass beads. All the other images are under a scanning electron micrograph, SEM. A scanning electron microscope, sorry, an SEM. But these are quite big particles, relatively speaking. They are, I think, the median size. They're pretty mono-sized particles, and the median size was something in the order of 55 microns. Okay. The concentration varies here from 10%, C equals 0.1. So I better use 0.1 rather than percent, and goes up to 45%, or C equals 0.45. And you'll notice that the apparent SOTA mean diameter varies from something in the order of just below 80 microns and eventually ends up something pretty close to our 55 microns that we can see from the picture here. But importantly, though, you'll notice that there's a gradient. Okay, so we're going to use a single value in the model for our SOTA mean diameter, which would be the 55 microns. But clearly, actually, a better fit to the settling data would be something that is a function of the solid's concentration. In other words, you get a surprisingly faster settling velocity at 10% than you would predict. And that surprisingly faster settling velocity gives the particle size to be bigger. Okay, whereas really, if we had a value of SOTA mean diameter that was valid across all the ranges, and it gave the correct settling velocities, because these values here have all been deduced by rearranging the force balance to work out the force balance and the Happel and Brenner equation combined. So they've been rearranged to work out what x is from u0. Okay, this is what x is from u0 from the observed settling velocity in batch sedimentation. All these are experimental data. These data points are all experimentally measured data, and a lot of them, they're replicate tests. Okay. Well, the good news is, if we were to use this value in our design, it's actually going to give us an overestimate of the required area for the design. So there's no disadvantage by using a low value of particle size in the equation, whereas arguably a higher value of particle size might be more relevant if we're operating under just a restricted range of concentrations. So to use the minimum particle size is going to give us a bigger area, but that's safe. We don't want to be the other way around. From a design point of view, we're erring on safety. We're building in what should be a safety margin. So, okay, these are glass beads, spherical particles, very incompressible. What about some more realistic material? Well, we have here calcium carbonate in the form of calcite. The mineral type is calcite rather than aragonite, and what we have down here is a scale bar which is 10 microns in size. So these particles are a variety of different sizes, somewhere around about the 10, slightly above the 10 microns in size. Same thing done over here as we did with the Ballatini. We measured a whole load of settling velocities, reworked the equation, the force balance equation and the permeability to give us the particle size. And we have particle size plotted here against concentration again. So here's against concentration, and again there's lots of data points, this time going from 5% or C equals 0.05 up to C equals 0.45. Again, we have apparently larger particles at the lower sizes. That's 0.1, that's 0.2, that's 0.3. The interesting thing is it's plateauing. It is plateauing to arguably what we should expect the SOTA mean diameter to be in a consolidated bed. Okay, so long as our Happel and Brenner calculation came up with, or we put into the Happel and Brenner calculation a value of, that is, let's say that's 12.5, 13-ish microns. So down here we've got a SOTA mean diameter of 13 microns. So long as we put 13 microns into the Happel and Brenner equation and then into the force balance, it would give us again a slower settling velocity than any of these other sizes. So again, we're doing a safe design by overestimating the amount of required area for our thickening to take place. Now, is 13 microns a sensible value? It probably is. Looking at these images here, if that's 10 microns, 13 microns is probably a realistic realistic diameter to use for our SOTA mean for these particular particles, just as 55 was a reasonable one for these particles. Two more materials then. This is dolomite. Dolomite is a calcium magnesium carbonate. It's a mineral that's been crushed. Again, we have the 10 micron scale bar down here in the SEM, and you'll notice a vast amount of very fine material. So this material is very angular. It certainly has some bigger particles than 10 microns, but it has a huge amount of very small particles. So there's a really wide size distribution for this material. It doesn't go up to particularly high values, but it's got some really small particles. Again, we have the SOTA mean diameter plotted here against solids concentration plotted here, and these are values of the SOTA mean diameter as deduced from the force balance and the Happel and Brenner permeability equation in that force balance. So we have values going from 0.05, just like the calcite, to, in this case, 0.4, 40%, 0.4. I think it was possible to go beyond 0.4, but we were no way were we in the constant rate settling period. There was clearly compression going on in those tests. So what is the plateau value? We haven't quite made it to a plateau value, but the plateau value would be something in the order of 10 microns, maybe slightly less than 10 microns, maybe something in the order of, say, 8 microns, which, bearing in mind this is a SOTA mean diameter, 8 microns would be about there. That's reasonable. Looking at the particles in the SEM, 8 microns, willing to believe is a fair value to use as the SOTA mean diameter to give us the particle size at that concentration. And what about the last mineral that we have here? Again, the SOTA mean diameter against concentration. That's for the mineral talc. Talc is a very unusual mineral, or it's a clay-like mineral, which has a plate-like surface. So end on, you see a very thin plate, but the actual plate itself, looking head-on, would be much bigger, and that's what you see here. Plus, these are aggregates of these platelet-like type minerals. I mean, here you can see there's one that's edgeways on. This is one looking face on. Again, we have our 10 micron. What are we plateauing to here? Well, we've well and truly plateaued actually at 6 microns. So here is the SOTA mean diameter for the material. That's 10 microns. That's obviously way above 10 microns, but talc, when it's dry, does tend to stick together. Dispersing talc is a very difficult thing to do at the best of times, and certainly dry it does stick together. And don't forget that that is a thickness of something in the order of 1 micron. So we've got a 1 micron thick, albeit maybe a 10-ish micron diameter. So 6 microns is not a bad representation there of what we expect for the particle size. Again, well, it should give, if we were to use 6 microns in the Happel and Brenner equation to work out the permeability and therefore the settling velocity, that should give us a perfect match for the settling velocity at that concentration, not too bad at that concentration. It's only that concentration where the settling velocity would be significantly underestimated, and as I said before, that's the right way to be for a design. If we're underestimating the settling velocity, and in fact the settling velocity is greater, then the whole thickening process should be a lot easier. So it's safe to stick with that underestimation of the velocity. So a bit of a review of alternatives here, and just a bit of a recap that we're looking really for the settling velocity, u0. We know that it's a unique function of concentration. However, getting a constitutive equation for that is potentially difficult. Kozeny-Kármán we don't like because it has the Kozeny constant in it. And in loosely packed beds, moving beds, 5 is not really a good value to use at all. Happel and Brenner we like because it's a purely theoretical model, solution to the Navier-Stokes equation with no fitted parameters, so that one doesn't suffer from the problem of really having to do some experimental work other than knowing what the particle size is. Whereas for the other techniques we'd have to work out the Kozeny constant, or if we were going to go the permeability route, what the value of n is if we were to use Richardson and Zaki's equation for permeability, because it can be done. You have an option here using Richardson and Zaki's approach. You can either use it in the same sort of way where this is then put into the force balance, which would give us a value of k, which we can then rearrange to give us a particle size, or alternatively you could just ditch that altogether and not bother with permeability and just say here is our equation for u0 equals a function of concentration. So there is two approaches to the Richardson and Zaki way. However, you're stuck with that fitted parameter, and the only way of getting that realistically is to do some tests, and for the simulation on the website we can't rely on those tests having been done. So it's true to say that the Happel and Brenner approach is the one that we prefer, but you do need a good particle size distribution because it's very easy to miss the fine material when conducting a particle size analysis. So you need an instrument that picks up the fine material, because they'll have a lot of surface area causing a lot of hindrance to settling. Modern instruments actually are quite good at that. It's the older style instruments that weren't very good at it. So we do need a reasonably, well, a good accurate SOTA mean diameter measurement. In the future, there's a possibility that discrete element modelling with computational fluid dynamics, DEM with CFD, will be able to model the whole process. It's wholly dependent on a lot of computing power. Having done a recent survey of the literature, I don't think we're there yet. There's great leaps being made forward in the modelling of particulate processes using DEM coupled with CFD, but by no means is it something that lends itself to a design at this stage. So where does that leave us then? Well, there's the website. On the website you put in some inputs of SOTA mean diameter, in this instance 50 microns, so these particles are going to settle pretty quickly. Some density information, the desired underflow concentration. Don't forget you have to be able to pump it, so don't put a particularly high value in there. The feed concentration, here it's 2% or 0.02 by volume fraction. And of course the feed flow rate. So putting those values in, everything else is calculated, the underflow rate, the overflow rate, and in the classic Cohen-Clevenger style we then have a range of thickener areas and therefore thickener diameters, because we're using the fact that it's looking down and it's a circle. So we've got the area is pi d squared over 4. Okay, that's the area there. So clearly we're rearranging from the thickener area pi d squared over 4 to get the thickener diameter, and then the software is simply looking to see which is the largest area. So this is designing based on the feed concentration. This is applying Cohen-Clevenger's equation on the feed concentration. This is 1 up on the feed concentration, 0.3. This is 0.4, 0.5. You see that basically the lowest flux handling ability is at the feed concentration, and therefore the diameter of the thickener should be, let's say, 23 meters in diameter, because that is the largest area that comes out of the design. So that is the basis behind how we now do the simulation on the website for continuous hindered settling, now using the permeability expression due to Happel and Brenner, as well as the Cohen-Clevenger approach to continuous thickener area.